Hello? Sweet. Right, let's get started. And it's very exciting to start our second day with this talk on language agents. So for anyone who is working in the AI space in the past year or so, you probably will agree with me that this is now a very chaotic space, right? Exciting, yes, but also very chaotic. So we have to ask, like underneath all this chaos, whether there is something fundamental that is meaningful that is going on that will probably stand the test of time. And hopefully, the topic we will discuss today will be one of them. So, there won't be too much math or any equation at all in this talk. So we won't consume too much of the morning caffeine you just take in. But it's really just to share these fresh ideas with you. And because this field is so moving so fast and it's so new, so many of the ideas and opinions here are bound to be speculative. So take it with your own discretion. Right, so what is language agents? These agents are usually built on top of large language models. But instead of this typical question and answering style behavior of language models, they are connected to real-world environments to the extent that they can autonomously carry out non-trivial complex tasks in different environments. Right? So we have seen a lot of such examples lately. The most famous one is probably LLGPT. It was released just 5 months ago. But just to show you the crazy level of public interest on this, just in 5 months, AutoGPT has got over 150,000 stars on GitHub, making it the fastest growing GitHub repository in the history. Right. But despite this, we know these are really just proof of concept efforts. There are many known and oftentimes serious limitations of these efforts. So we have to ask, as researchers, why? Right? This concept of agent has been here for forever. Right? It's one of the first concepts we teach in AI 101. So what's different this time around? Right? Why all of a sudden it becomes the new trend in the town? So I argue that the fundamental change here is really now these agents, because of large language models, are equipped with a kind of universal capability of using language as a vehicle for both thoughts and communication. And this trait was unique to humans before these artificial agents. So it's obvious that these agents use language for communication. In fact, ChatGPT, right? We know as a fact that ChatGPT was, in terms of the foundational capabilities, not so much better than its earlier versions. It's just that OpenAI fine-tunes ChatGPT to make it more chatty and release it to the public so then people can just chat with it about everything and then realize, hey, these models are fantastic. So that directly contributed to the viral success of ChatGPT. But perhaps this capability of using language for thoughts is a bit more unique in this current generation of agents. By the way, I will kind of have to use or to anthropomorphize this agent a little bit because it's just so much harder if we have to try to come up with another set of terminology to describe their behavior. Okay? So chain of thought is a good example of this capability. With chain of thoughts, instead of directly generating the answer or directly generating the output given input, now these models are first instructed to generate some thoughts, right? Okay. So the thought may be the cafeteria had 23 apples originally, blah, blah, and therefore the answer is 9. So instead of directly generating that, the answer is 9. Okay. This seems trivial, But why that's a big deal? Let's consider this simple example. This was a viral example on social media. It's generated by GPT-4, and many people were laughing at it because they think GPT-4 was being stupid and contradicting itself, right? But what I'm seeing from this example is actually the power of thinking in language, right? Now, because these AI models, different from the previous versions, they are not just a simple functional mapping from input to output anymore, right? That they are capable of generating these thoughts, this language, before arriving at the answer. So that gives them the opportunity to correct themselves, which was not possible before. Maybe this one is still too simple, so let's consider another one, a much more complex one. Here we are testing GPT-4 vision. It just became available very lately. And this question is fairly complex. It's about, okay, we are introducing a virus to control a rabbit population. We introduce the virus here. So it has both text and image, right, because it's GPT-4 vision. Then this curve shows the population change of rabbit. And as some distraction, we also show some rainfall statistics. But if you actually look at the data, the rainfall statistics is not correlating with the rabbit population. So it's mainly as a form of distraction. And then what's really going on here, so this is a multi-choice question. So there are 5 options. But eventually it comes down to 2 most plausible options, B and C. B is talking about natural resistance, natural immune. And then C is about acquired resistance, right? So if we look at the curve here again, you can see that the population quickly dropped to a minimum, but then quickly bounced back. So that usually suggests that there is some inheritance. And we know that acquired resistance is not inheritable. So therefore, it has to be natural resistance. Okay, so you can see how complex this question is. Like, even for me to explain it, it takes quite a while. So now let's see what GPT-4 vision does. Right? It's first doing some analysis about the question and the image, and the corrected identify that the rainfall here is just distraction. And then it goes on to analyze every option carefully. And then B and C are most plausible, but the main difference is natural versus acquired resistance. And then eventually finds the correct answer, B. Okay. So if this is not like some example of kind of thinking in language, I don't know what it is. Right. So this is my favorite slide. I hope if you have to take one slide with you after this talk, this could be the one. So to further see why language is such a big deal, let's consider an analogy in the biological intelligence space. We know language plays a critical role in human intelligence. So many animals are intelligent. We know that. Mouse here can learn to navigate a maze, right? And pigs are very intelligent. There are many, many animals that are intelligent, right? But their intelligence just pales in comparison with human intelligence. And even though humans and other animals can think without the language and the associated acquired linguistic representation just increase this power immensely, right? So with the language, we can think counterfactually and prefactually. We can like record our transient thoughts for deliberation. We can communicate with each other our beliefs and thoughts. And then we can write down knowledge to pass them down for generations to come, right? So in the millions of years of evolution of humans, the history of language is a very small part, especially written language. It probably has a history of like 5,000 years. But it's within these 5,000 years that the human intelligence and civilization saw an exponential growth, right? So maybe, just maybe, AI may be at a similar inflection point. It seems that artificial intelligence is following a similar evolutionary path. So the agents from previous generations like this can be trained repeatedly to be able to to do some very specific task, like playing an Atari game from DeepMind. But now these language agents, they are starting to show signs of broad and flexible and very complex task-solving behaviors. Here is one question I was asking, I think ChatGPT at the time, about, it's probably too small. Like, it's a prefactual question. The question was, if we had room temperature superconductor, what would it mean for artificial intelligence, right? So the model probably has not seen too much of this text in its pre-training corpus, but it was able to generate like a long list of very plausible points about this prefactual scenario. And I checked every one of them. They all make sense, at least to me. Okay. So that's some background about language agents. Then how do we conceptualize this? Here's my attempt. At a high level, we have an agent that optionally has an embodiment and that can interact with some environments. So it's very similar to the classic agent architecture. But what's really different here is within each component and how they interact with each other. In the interest of time, I'll just maybe touch on two aspects here. The first is on the agent side. Now these agents, I think they are equipped with a very interesting and powerful memory mechanism, with both in like working memory and the long-term memory, that provides a very versatile and powerful foundation for reasoning and planning behaviors on top of them. And we will drill a bit deeper into that later. Then on the environment side, right? So it used to be the case that if we want some agent to work with some environments, we need to hand wire that environment into the agents. And oftentimes we need to do all sorts of simplification in that process, right? And we have to do that one by one. And usually an agent can only work with one environment. But now these language agents, thanks to the power of large language models and the capability of using language for thoughts and communication, they can interact with heterogeneous environments, multiple of them, on the fly to solve complex tasks. So to do that, they really need to understand like the input and output formats of each environment, like a relational database, the web, and so on and so forth, and also the semantics of that environment to be able to ground its own intent into those different environments. Okay? And because of this, now these multi-agent systems are really also seeing some very significant changes, right? It used to be the case that for multi-agent systems, we have to predefine like each agent and maybe some basic framework of how they interact with each other, and then what you're learning is just a policy under that framework. But now, because as you probably have seen work like the generative agents from Stanford, for example, this space of multi-agent systems are seeing a lot of new opportunities. Okay? So next, I will touch on maybe two aspects of language agents. The first one is memory, and the second one is grounding. The memory in all of these language agents, I think the memory is probably the most intellectually stimulating part for me, even though it's not the most fancy part that people out there are working on. I just find it's very intriguing to think about the similarities between the machine memory and the human memory here. Let's start with the basics. So regarding the mechanism for storing memory, right, there are a lot of similarities. We know animals store memory through the so-called synaptic plasticity, right, which means that you can change the strength of some existing synapses, or you can even remove existing synapses or grow new ones, which is very important for long-term memory. Then artificial neural networks and neurons, they also store information in their weights, right? Analogous to synaptic strength, right? So this really shouldn't be a surprise because these artificial neurons were designed to mimic their biological counterpart in the first place. But I think this biologically inspired roots of AI is not at the center stage of discussion these days, which I think we really should talk about them more. Okay? Then the in-context learning capability of these language models has a lot of similarities to working memory of humans. Right? First of all, in in-context learning, there's also a scratch pad that can temporarily hold the information, right? And there is a mechanism to reason over that information, just like working memory. And also, interestingly, attention plays an important role in both of this. Right? We know in working memory, selective attention plays a very important role. And then in context learning, we know that this self-attention in transformers is very important. When it comes to long-term memory, the picture becomes a bit more complex. So many people out there think that a vector database with retrieval augmentation would constitute a long-term memory for these agents, right? So the agent can have some experience, and then you store those, you vectorize those, those as episodic memory, and you store it in external vector database, and at test time, you just retrieve from that, right? So is that really long-term memory? Or is that similar to the long-term memory of humans? I think we know humans' long-term memory is much more important than that, right? It's highly structured, it's distributed, and it's probably compositional. So, and when we're using the memory, retrieving from memory, it's probably not just like doing vector matching and retrieving from a bunch of vectors, right? So in that regard, this recipe around vector database is utterly unsatisfactory as long-term memory for these language agents. And I think these language models' parametric memory, in that sense, is probably much closer to humans' long-term memory. Right? That leads us to the next point, why these language models can understand and generate language in a kind of a universal way. So my conjecture here is that these language models may have internalized a compact and compositional linguistic representation by compressing its pre-training corpus, similar to how humans learn and memorize. Right. So this learning as compression idea has been there for quite a while, and is one of the leading theories around LLMs learning. But if we think about this, so both a language model and human brain are information systems with a limited capacity. Right? And during learning, they are under pressure to form this compact representation. The pressure here for humans is probably survival, of course, and also mating. And then for these language models, the pressure comes from they have to universally predict the next token. when you can do this simple thing universally well, you have to have not just like statistical parrots, but you have to have more compact distributed and compositional representation. So that's just my conjecture. But we are starting to see more and more evidence of this. And I can share some pointers if interested. That also leads us to the next question, another controversial one. So can a language model truly understand a concept like apple without actually seeing the physical object during training? Right? Essentially, if you don't have grounding in training like humans do, like especially when we have embodiment, then is there true understanding? Okay? So I used to hold a similar view, but now I'm more inclined towards an alternative theory, which I tentatively call it the textual twin word theory. It goes like this. If a language model or any AI model can understand a concept like apple in this pure textual form, by the way, all of these are generated by ChatGPT and just one shot. And then you can also understand all the associated concepts used to define that concept, like what is round shape, what is red, and so on and so forth. Then these interconnected concepts may form a concept network that is maybe isomorphic to that of the physical world. And that may allow these models to unambiguously understand a concept without actual grounding. Remember, these text data that these models are trained on, they were derived from the physical world in the first place. So that may build the isomorphism in the first place. So there are a lot of room for arguments. Like you may argue that how general this is, or this is a cherry-picked example, or whether isomorphism is really a very strong condition for understanding. But the points I'm trying to make here is that maybe grounding is not necessary, maybe not a necessary condition for these models to understand. I still believe that grounding and multimodal training will bring a lot of benefits in terms of learning efficiency. Maybe you will be able to, if you have grounding and you do that in a smart way, then you can learn like orders of magnitude faster. But it may not necessarily mean that the theoretical upper bound of what you can learn will be different. But of course, there are still a lot of things that you cannot express in text, like how to ride a bike, right? This kind of implicit memory. But for the things that can be verbalized, maybe that's the case. Interestingly, the other day I was talking about this to an audience with philosophers and the linguists in the audience, and they pointed out that decades ago, a philosopher, Wittgenstein, in his famous work, Philosophical Investigations, expressed some similar ideas, which essentially boils down to that concept networks can give meaning. So meaning doesn't have to be referential in nature. Okay, let's check on time. All right, we have some time. So for the rest of the talk, I will discuss another very important aspect of language agents called grounding. Because the language agents are about connecting these language models to real-world environments, and each such environment serves as a unique context to interpret the natural language. So that makes grounding a central topic for these language agents. Grounding is a highly overloaded term, and in the history of AI, it's mostly about symbol grounding. But I think in this context, there are two main types of grounding we care about. One, we want to ground these language models in these different environments. And we will see the exact definition of that in a bit. And two, because these agents will receive perception from these environments in the form of text or other modalities, then we want the subsequent behavior and like generation and actions of this agent to be grounded in its context, its working memory, which contains information from this external environment as well. Okay. So for the rest of the talk, I will cover these 4 recent work, but I will only touch on them very lightly. The first work is about Mind to Web. It's about building a generative agent for the web. And then we will talk about embodied agents, what happens when you connect them to large language models. And then finally, I'll talk about a more general proposal for grounding these language models to different environments. And then in the end, I will talk about how these language models behave when they are presented with external information. Okay, so before we start, let me just try to give, this is the only equation in this talk. Let me try to just formalize things a little bit. When we talk about being grounded in an environment, this is what we mean. So given a natural language utterance U and the target environment E, we want to produce a policy that can map U to a plan P such that the denotation or interpretation of the utterance in the environment E is equivalent to that of P. Right? So in other words, if you execute P in that environment, it would produce the desired environmental state dictated by the utterance. Okay? And the environment here could be vastly different. So if the environment is a knowledge base, then maybe the plan P is in some query language like Sparkle, or here we're using a Lisp-like language that can be deterministically mapped to Sparkle. Or if the environment is websites, web pages, then the plan could be like some typing and clicking on different elements on the HTML web page. Or if the environment is a physical world and you have an embodied agent like a robot, then the plan here could be these atomic actions like that. So the challenge in this general problem space is that different from just text generation, now you have an infinite number, you have very diverse environments as you can already see. And even for the same type of environment, there could be an infinite number of them. Like just think about all the relational databases out there in the world, right? And then even for the same environments, there could be an infinite number of environment states, right? Like you can remove or add information to a relational database all the time, right? So all of these together just makes it very hard, if possible at all, for just simply pre-training a language model to handle all of that. Okay? So now the first work, Mind to Web. Here our goal is like this. We want to build an agent that allows you to just hop on any website, real-world website, not simulated, and then you can just say whatever you want. And the agent will hopefully understand the utterance and understand the website, even though it has never seen it before, and then just do the thing for you. Okay. So you can book flights, of course. That's the canonical example everyone uses. But you can book flights on all different websites, like United, AA, Delta, and so on and so forth. And then you can also, I don't know, schedule an appointment for car knowledge test on DMV. So there are a lot of such things that it's just hard for us to figure out how to use each of these websites. And if there is an agent that can automate away these tedious tasks for us, that'd be great. So let me, too flashy, so let me stop it here. But the challenge here is that, well, there's a billion of different websites out there, right? So it's highly heterogeneous, and different websites can be developed in different ways. And also, these websites, they are usually following a reactive style design. So that means the next web page is dynamically rendered based on the action you just take. So this is a partially observable environment. And these websites are just so complex. Right? If you just look at the HTML code and you ask a language model, hey, this is the HTML of the website, then this is the utterance, what should I do? Then the language model will struggle a lot with that because it's just too long and too noisy. Right? So some of the approach we have taken, explored here, is to have some collaboration between a small language model and a large one. So the small one will be more specialized, and it will learn to filter, look at each web page and filter what are the plausible options, actions, or HTML elements I may take. Then the large language model like GPT-3 or 4 will deliberate over those options. That's one thing. But recently, what we have been trying is to use these large multimodal models like GPT-4 Vision, right? Which is very natural because these websites, they are not designed to be read in HTML, right? They are designed to be rendered in visuals for human consumption. So understanding these visuals is much easier than the HTML. And the performance from GPT-4 Vision is great. Okay, so in the next work, I'll talk about embodied agents. So what happens when we have an embodied agent connected with a large language model? The motivation here is very clear, right? So for a long time, we have wanted these robots that can handle a wide range of tasks instead of a few pre-programmed ones. And then large language models may provide this capability for them to quickly understand this diversity of tasks and to operate in different environments, even new ones they have never been trained on. Okay. So here's how it works. Given a task, then this is a prompt to the language model. And the language model will generate a high-level plan. Okay, so you want to first navigate to a potato, then pick up the potato. Then we have a low-level controller that will turn each of these high-level actions into low-level plans, and then execute in the environment. One interesting here, the agent cannot find the potato in the environment because it turns out the only potato in the environment is stored in a closed fridge. Then we dynamically prompt the language model again, and because these language models, they have some sort of common sense knowledge. They know that food is usually stored in fridge. Then they will generate dynamically this rectified plan that asks the agent to first check the fridge. So this is the dynamic grounding aspect of it. Another aspect that may be worth noting here is this is very representative of these grounding tasks. That is, there's a very strong environment dependency, right? If you just think about the planning task here, okay, given the utterance, if you directly generate a low-level plan, like turn left, turn right, this low-level plan is highly dependent on the environment to the extent that in a slightly different environment with different positions of the object, then the low-level plan could be vastly different. So what we do here is this hierarchical planning, where we first generate a high-level plan, like this one. And then once you get to the high-level plan, these high-level actions, like find a potato, becomes a classic object localization problem that you can tackle separately with a low-level controller. Okay. Running out of time, so let me very quickly touch on this. So for Pengu, you just really need to understand this simple example. But I asked you this question: find the right program over a knowledge base. and I'll give you 3 options. I don't tell you the syntax or semantics of the query language here. Then if you stare at it for long enough, you can probably conclude that the second option is the most plausible. Because, well, the third one is about the hockey team, which doesn't mention like coach. And the third one is about some cricket. So then the second one must be the correct one. But on the other hand, if I ask you to directly write down this program like this, then it will probably be much harder. Why? Because now you need to learn the grammar of this programming language, and you also need to know the environment specifics. Like how exactly is this entity or relation represented in my environment? So that's the same thing for language models. Typically, people would just use a language model in their conditional probability formulation. So you just auto-regressively generate one token at a time. But now we are arguing that for this type of task, maybe that's not the best way of using language models. Maybe we want to go back to the original definition of a language model, which is just a model that assigns a probability to a sentence. Right? So we use this joint probability formulation of language model. And then we use this language model as discriminators instead of generators. And here's our framework. You have a symbolic agent that is operating in the environment. This agent will incrementally explore the environment and incrementally generate valid plans. So it's a search process in the environment. And then the neural language model comes in to score these plans, to guide the search process. Right? So it tells the agent where to go next. And it turns out this simple idea provides a very generic recipe for these kind of grounding tasks. So as I said, it's very simple to the extent that the pseudocode really only has 4 lines of code. So you do a for loop, and then at every step, you just generate some candidate plans based on the environment and your previous plans. And then you use the language model to score them and find the top K. So it's like a beam search process. And then if the termination check passed, then you return the top scored plan. Otherwise, you keep going. Okay. Here's a simple demo on the task of knowledge-based question answering. This is an ideal test bed for this task because these knowledge bases, they are gigantic, right? The one we use here has 45 million entities and 3 billion facts. So if you just do autoregressive generation with language models, it will fail miserably. You can see we start from some initial plan, maybe the topic entity identified in the sentence. We explore the surrounding, find some initial plans, score them, find the most promising one, and then further explore that area to get more complex plans. And then this process just keeps going. So I won't talk too much about the results, but it's fair to say that with this simple idea, it was sufficient to set a new slave of ours on all these popular KBQA benchmarks. And for the first time, we showed that we can also use large language models with in-context learning, just a few examples, for a complex task like KBQA. Okay. So I'll spend maybe 3 minutes to talk about this last piece of work, like how to do grounding in context. Right? So we know that these, the parametric memory of language models, they are static, they can become stale, and then it's very natural to augment them with external information, like whether from a retriever or from some other tool augmentation. So in this example, this parametric memory was not just stale, but it was also wrong. Like Demis Hassabis was never chief scientist of Google DeepMind. Then the question we ask is how receptive are language models to this external evidence, especially when that conflicts with their parametric memory. So we call this conflicting evidence as counter memory, and we want to see how language models react to them. So we take a behavioralist approach here, just try to examine the behaviors. right? So there are two examples. Sometimes the parametric memory could be correct and the counter memory could be wrong factually. And sometimes the parametric memory could be wrong and the counter memory could be correct. I won't talk about the details here, but I just want to say that we spent a lot of time trying to make sure the parametric memory we're examining is indeed the firm parametric memory of language models, and the counter memories we're using are indeed contradicting with the parametric memory. So we designed a lot of checks just to make sure about that. Okay, so here are some interesting observations from this study. The first observation is when we only show one external evidence in the context, that is the counter memory, right? So this is the only thing we show to the LM, and it's directly contradicts with its parametric memory. Then it turns out that these language models are highly receptive to such external evidence. If you look at these two sets of bars here, so they would most of the time select the so-called counter answer instead of its memory answer. And what's even more interesting here is that, so people have looked at similar problem before, but what they did was fairly simple. They do the so-called entity substitution. They just find subtopic entities in the parametric memory and replace them with some incorrect entities, like lemma. But because of the majority of the passage will still be about pairs, so it renders this parametric memory to be logically incoherent. And then if you just do that, it turns out it's very easy for these language models to detect that this is not coherent, therefore it's not trustworthy, and it will just discard that. However, if you use our pipeline to generate this coherent and convincing counter memory, then it becomes very happy to just accept those. So there is also like safety implications from this. Like that it also means that language models can be easily deceived by adversarial tools. We also show that these language models show confirmation bias. If you just present multiple pieces of evidence to it, and some of them are consistent with parametric memory, some of them are contradicting. And then in contrast to the previous observation, now they will tend to stick to their parametric memory. Okay, so I'm a bit over time, so let me conclude here. So what is the journey ahead of us? As many people are saying, is NLP dead or is NLP soft? Personally, I think absolutely not. I think it's the most exciting time for NLP ever. However, instead of natural language processing, maybe it's time to move beyond that. Maybe it's time to think about natural language programming. Because these large language models and language agents, they're really starting to turn natural language into an unprecedentedly powerful programming language. Right? That is much more expressive than any of the formal programming languages out there. So maybe we should shift the focus of our field to this next. And I hope that in the not too far future, everyone can have this personal assistant that sit on top of everything to automate away a lot of tedious tasks in our life. Thanks, and we will be giving a tutorial on language agents at EMLP, so you're welcome to join us there. Thanks for the sponsors, and happy to take questions.
So unfortunately, as we're a little bit over the time,